This explanation for polymers is way easier to understand than most textbooks.
Welcome to this exam review explainer. Look, if you're gearing up for your CSEC chemistry exam, you probably know that organic chemistry, specifically polymers and linkages, can kind of feel like a massive puzzle with way too many tiny pieces. But hey, don't sweat it. We're going to organize that puzzle today. Okay, let's dive into this. We're setting a high-energy, focused tone right out of the gate so we can master polymer chemistry once and for all. By the time we wrap up, you'll be spotting those chemical bridges way faster than any examiner can try to trick you. Here's our study roadmap for today. We've got 1. Polymerization fundamentals. 2. Recognizing functional groups. 3. The condensation process. 4. Polyamides versus polyesters. 5. A practice exam question. And 6. Final exam survival tips. Stick with me through this structured explainer, and I promise you'll get the cheat codes to ace these questions. Let's hit it. Moving to Section 1, Polymerization Fundamentals, Building Giant Macromolecules. Because before we tackle the really complex chemical bridges, we've got to start right at the foundational level of how these giant molecules are actually put together. Think of a single paperclip, right? On its own, it's just a small, basic unit. Well, in chemistry, we call that single unit a monomer. Now imagine hooking 50 or even thousands of those paperclips together to form this massive chain. That whole process? That's polymerization. The CSEC syllabus specifically defines this as the process of joining 50 or more small units, those monomers, to form giant macromolecules. Now pay attention to that magic number. 50 or more. That is absolutely crucial. We aren't just talking about slightly larger molecules here. These are massively huge structures that make up, the plastics in our pipes, the proteins in our muscles, the nylon in our clothes, the whole shebang. And this brilliantly illustrates the two main ways we actually build these giant chains side by side. Addition versus condensation polymerization. Let's break it down. With addition polymerization, you need monomers with unsaturated carbon-carbon double bonds. The process is pretty straightforward. Those double bonds literally break open, the monomers join hands, and boom, you get a long backbone of single carbon-carbon bonds. Notice how absolutely no atoms are lost here. They just rearrange themselves. But condensation polymerization, totally different story. For this, we need monomers with two different functional groups. When they join together, they actually eliminate or spit out a small molecule, which is usually water. And doing that creates unique chemical bridges like amide or ester linkages. On to Section 2, Recognizing Functional Groups, Identifying the Sticky Ends. Now that we know the two main types, we really need to look closer at the building blocks themselves. Recognizing specific groups is absolutely key to identifying the whole polymer. Let's look at the anatomy of an amino acid monomer, which, spoiler alert, is incredibly common in CSEC questions. Think of this molecule as having two sticky ends that just desperately want to grab onto other molecules. Over on the left side, we have the amine group, written as NH2, and on the right side, we have the carboxylic acid group, written as COOH. Because these two ends are distinctly different functional groups, they are primed and ready for condensation polymerization. They are your crucial reaction points. Okay, listen up, because here is a direct, incredibly important exam tip for you. When examiners write out the formula NH2-CH bracket R bracket dash COOH, students almost always panic when they see that R in the middle. Don't let it trick you. That R is literally just a variable side chain. It's nothing more than a placeholder that makes each amino acid unique. Think of it like giving a different paint job to the exact same model of car. So when you're trying to figure out how the polymer forms, just completely ignore the R. Just scratch it from your mind. Focus entirely on the reactive sticky ends on the outside, the amine and the acid, because that is where all the chemical magic actually happens. Which brings us to Section 3, the condensation process, building the chemical bridge. We found our sticky ends, so let's watch the actual chemical reaction take place step by step. Let's move to this sequence and see how it builds. Picture two amino acid monomers bumping into each other. Step 1, the sticky ends meet. The amine group of one monomer aligns right up against the acid group of the neighboring monomer. Step 2, they eliminate water. The amine group donates a hydrogen atom, and the acid group donates an OH group. H plus OH gives us H2O. They physically spit out a water molecule, kind of like it's sweating from a microscopic workout. And finally, step 3, because those atoms just left, the remaining carbon and nitrogen are forced to bond together, creating a brand new chemical bridge. And there it is, the amide linkage, written as -CONH-. Moving right along to Section 4. polyamides versus polyesters, avoiding the classic exam trap. Examiners know these condensation polymers look super similar on a printed page, so this is a critical warning about a common pitfall. I need you to channel your inner visual detective here. When you're staring at a long polymer chain diagram on a test, look straight at the linkage bridge. For polyamides, how do you spot them instantly? You look for the nitrogen. Polyamides contain that CONH linkage we just built. If you spot an N, boom, you have an amide link. Then, on the other hand, we have polyesters. Polyesters are formed from an acid and an alcohol, so their linkage is just COO-. There is only carbon and oxygen, literally no nitrogen whatsoever. So, rule of thumb, nitrogen means polyamide. It really is that simple. Now, another concept that really trips students up is the origin of these polyamides. We have natural and synthetic versions, but chemically, their bridges are totally identical. Natural polyamides are the proteins inside your body, formed biologically from amino acid monomers. Synthetic polyamides, on the other hand, are man-made in a factory. Think of nylon, which we use in textiles and ropes. But here is the critical part to remember. Whether it was built naturally in human muscle tissue or built synthetically in an industrial factory, both proteins and nylon share the exact same CONH-amide linkage. The origin changes, sure, but the underlying chemistry of that bridge remains exactly the same. Next up is Section 5, Practice Exam Question, the boss fight. You've learned the theory, you've seen the structures, so now let's apply all of this to a real CSEC multiple choice question. Let's go beat this boss. Okay, let's tackle this. The question asks, which of the following types of polymers may be derived from monomers of the type NH2-CH R-COOH? Your options are A, polyester, B, polyalkene, C, polyamide, or D, polysaccharide. Now, what's really interesting about this is that examiners are testing if you can distinguish between condensation and addition polymers on the fly. But don't worry, we have every single clue we need right there in the chemical formula. So let's walk through the logic step by step. Step 1, look at the functional groups. We clearly see an amine group and an acid group, meaning this monomer has two different sticky ends. This instantly tells us we're dealing with condensation polymerization, which completely rules out choice B, polyalkene, right off the bat, since that's an addition polymer formed from double bonds. Okay, step 2. What happens when an amine actually meets an acid? Well, they eliminate water and create an amide link containing nitrogen. This totally rules out choice A, polyester, because remember, polyesters lack nitrogen. And step 3, a giant chain of amide links is a polyamide. Therefore, the correct answer is undeniably C. See? When you systematically break it down using the sticky ends, it's actually pretty easy. Finally, Section 6, Final Exam Survival Tips, your chemistry cheat codes. We're going to do a rapid-fire wrap-up now to lock in the absolute most important takeaways from this review session. So the crucial point comes down to these 3 golden rules. First, if you see a small molecule like water being spit out during the reaction, you're looking at condensation polymerization. Second, if you see carbon-carbon double bonds simply opening up to hold hands with 0 atoms lost, that's addition polymerization. And third, when you're asked to identify a linkage on a diagram, always hunt for the nitrogen. If you spot that N in the bridge, you've got a polyamide, definitely not a polyester. I'm going to leave you with this thought as we wrap up this explainer. These invisible chemical bridges, the amide and ester linkages we've been talking about all day, they literally hold our biological and synthetic world together. From the structural proteins flexing in your hands as you hold your pen, to the synthetic nylon fibers in the backpack sitting right next to you. How many of these massive, microscopic polymer chains are you interacting with right at this very moment? It's pretty wild when you really think about it. Keep hunting for those functional groups, stay super focused on the visual clues, and you are for sure going to do fantastic on your exam. Keep studying and stay curious.
As always, the link for this study tool is in the description below. Let me know what you think in the comments.